the other exotica models.
Okay, so we're starting with the third lecture on the Higgs phenomenology and the BSM physics. So we're going to talk about the composite Higgs. So the composite Higgs, and then I'll also talk about the a little bit more exotic signals of the BSM in the Higgs couplings. So what we did in the first two lectures was we found that the experimental data are consistent with the standard model Higgs. However, the errors are still relatively large. Even so, this implies non-trivial constraints on the BSM model, so beyond the standard model physics. For instance, the perturbative standard model with 4th generation or 5 or 6 generations is excluded. Then constraints on we looked at the constraints on the minimally supersymmetric standard model. And when I introduced MSSM, there was a strong motivation for the light supersymmetry came from the hierarchy problem. Now what we'll do here, we'll talk about the strong interactions. The other solution, which is the strong interactions where Higgs is a composite, how you can think of it as either composite Higgs models, strongly interacting light Higgs, or the little Higgs. Now what I really spent time on is just the composite Higgs model. So we'll talk about the composite Higgs. So we have a Higgs who is a composite, is not an elementary particle anymore. The physics behind is the following. So let's say we have a strongly interacting sector which lives somewhere between, let's say, 1 TeV or 10 TeVs or so. It's well below the Planck scale, which is at 10 to the 19 GeV. And the strong interacting sector will have a spontaneously broken global symmetry. So whenever we have a spontaneously broken global symmetry, you'll have a massless Goldstone boson. And you see that you can use this to address the question of why is Higgs so light. Now what we're really addressing is why the Higgs is lighter than the scale of the strongly interacting sector, while the disparity between these two is just coming from the fact that there's going to be a logarithmic running of the coupling constants, right? So the question here will be, okay, if Higgs is a Goldstone boson, then it can be lighter than the scale of where the more complete theory becomes strong. Now why can it be lighter? Well, there's a shift symmetry here, where you can change Higgs to Higgs plus theta, and this symmetry, if it's there, you see it forbids the mass term. So this mass term is not invariant under the shift symmetry. Then the mass will come from explicit breaking of the global symmetry. So we have a shift symmetry which will forbid it, but there's also going to be the explicit breaking, and the explicit breaking will actually be just the Yukawas of the standard model and the gauge interactions. Okay. Now, if this sounds a little bit exotic, it's not, because we already have an example in nature of this type of theory, namely the pions in QCD. So if you ask why is the lambda QCD so much smaller than the Planck scale, you would say, well, it's because the way you can understand the lambda QCD where it arises is that you have the dimensional transmutation where you have a running of the alpha s, so the strong coupling constants. The Planck scale is way high up, so it runs down, and at some point it becomes strongly coupled. The QCD would become strongly interacting theory. You'll have a chiral condensate, it will break the what you have a global symmetry into the diagonal. So I spend a little bit of time on this spontaneous symmetry breaking that occurs in QCD. So if you look at the QCD Lagrangian and just look at the first two, the lightest two quarks, so the U and the D quark, if you can neglect these two masses, then you have a global symmetry, an approximate global symmetry, which is the SU2 left cross SU2 right. So the blue guys will form a doublet of the SU2 left. So now this SU2 left is not the electroweak SU2 left, it's just the global symmetry. And the U right and D right also form a strong isospin here, the SU2 right part of it. You see now this thing gets broken spontaneously down to the diagonal, where you have to change the UL and U right at the same time. The pions are the Gaussian bosons of this spontaneous symmetry breaking, and they're not massless as you would expect, because you have this explicit breaking of the symmetry. So a QCD is an example of this type of theories that I'm thinking of. Okay. Now, before I can go on to the composite Higgs models, I need to make a slight detour. So I need to say a little bit about the nonlinear chiral Lagrangian. So I'll open a bracket and start talking about something completely different. So I'll talk about chiral perturbation theory. So this part will be a little bit formal, but I need to introduce this formalism in order for us to understand the structure of the deviations of the Higgs couplings in this composite model. So once we swallow this formalism, it will be relatively easy to see the structure that arises for the Higgs couplings. So what we're talking about is spontaneous symmetry breaking of some global symmetry G down to its subgroup. So here's the global symmetry. We're thinking about the SON. So what's drawn here is, let's say we have a SO3 symmetry, so rotations in 3 dimensions, and this will get broken by, let's say that there's a field phi which obtains a wave in a particular direction, phi 0, so let's say that's in the z direction here. So the remaining symmetry is what? Well, since now I have a preferred direction, the rotation about the x and the y axis are broken, because if I rotate about the x-axis, I would move this vector. If you rotate around the y-axis, you would also move this vector. However, if you rotate around the z-axis, there is a remaining one-dimensional rotation. So you have a subgroup which is not broken. We'll call that H. Now the broken generators do the following. So if you operate with the generators on the wave of this field, this will be a non-zero action. So if you rotate around the x and y, you do move the direction of the wave. So these are the broken generators, and then there's one unbroken generator, the rotation around the z-axis. The usual notation that people use, or is used in this chiral perturbation theory, is that you split any element of the global group into the direct product of the broken generators times the unbroken part. So the U will now be an exponentiated form of the generators. Now the angles I wrote in a funny way. I plugged in a dimension-full field and divided by a dimension-full parameter. So this in a classical picture would just be the angle. And then the unbroken generator is just some other angle. So in this case, for the SO3, there's two broken generators. Okay. Now the SO2 example, what happens there? So let's say we have a Mexican head potential, the SO2 rotation, so we're living in 2 dimensions. The spontaneous symmetry breaking means that we sit in the minimum, so there's the field phi obtains a vector, it is pointing in a particular direction, so that's this blue point. And now what are the possible excitations of the phi field? Well, you can either excite it this way, so this would be a massive mode. You see that you have to pay a price of, if you pump in the energy, you need to pay a price in order to excite this field, so that will correspond to the massive mode. Now, however, if you excite the field such that it will go around the minimum, you see that I can make the excitation as small as possible, and you would still be able to have this long wavelength mode. So there's no mass gap. While in this other direction, since it's a harmonic potential, you see that there is a mass gap. All right, so that's a pictorial view, but I still want to show how you know that you have a massive massless Goldstone boson from this formalism they introduced, so that it doesn't go in way. Okay, so let's go through this formalism. The way you can see formally that you really have massless modes is the following. So let's take out these Goldstone bosons from all the other fields, like I have other fermions. Let's say in the QCD this would be U and D quarks. So I will factor out this Goldstone piece. In the Lagrangian there's also derivatives of these fermions. So now the derivatives will act on the U and the psi tilde. So the psi tilde does not contain the Goldstone bosons. And you can rewrite these two derivatives by taking a U in front, and then I have this remaining piece here. So I have U minus. So in the Lagrangian, well, it depends on psi and the derivative. You plug in the two forms. Now you see what happened is that there's a U sitting in front of the psi tilde. There's a U sitting here, right? So since I have a global symmetry, I can get rid of this rotation, right? The Lagrangian is symmetric with respect to the global symmetry. What I'm left with is the fields that don't contain the Goldstone bosons and the U, but with the derivative acting on it, right? So you see, so we learned two things, no? There's no mass term here. All the interactions of the Goldstone bosons have to go through derivative interactions. Right? It's an important result. No? We always couple through the derivative interactions. It has a shift symmetry, right? Because if you act with the derivative, here it's a global phase, this will cancel, so that's the shift symmetry I was talking about. And the pions are massless because of this shift symmetry. As I said, we'll obtain the mass from explicit breaking of the global group down the road. Okay. So, now the last piece of the puzzle is that there is an expansion here. So I have an effective theory. So instead of describing the physics in terms of this non-perturbative theory, we want to look at the particles which sit at the low energy. The particles which sit at the low energy are the Goldstone bosons. So we have a theory of Goldstone bosons or pions and their interactions. Now we already know how the interactions will look like. So if I look at the tree level and the one loop correction, well, what do we know is, at least if you use so we know that I have to plug in the derivative, so there's going to be derivative interactions. Each time you have a pion field here, there's going to be 1 over f squared there, so I have two derivatives will make a Lorentz invariant quantity, so I have p squared for the first term, to have something dimensionless, and factoring out all the other terms, it's an O of f squared. Now you go higher up, again, there's two derivatives here. In each vertex, at least two derivatives have to arise because of the Goldstone boson nature. So the next term will be of the order of p squared over f squared times the loop factor, which is 1 over 16 pi squared. And this description will break down once the one loop is as large as the tree level. So if you have an energy which is of the same size as 4 pi f, the expansion will break down. So we learned two things. I have an expansion in energy, and the expansion parameter is E over 4 pi f. So the UV scale of this effective description is 4 pi times this f, the dimension for parameter that I plugged in. Okay? Right, so now I can close the bracket and move on to what we're really interested in. So we're interested in composite Higgs. And you'll see that the story will be, by now will be familiar. I'll assume that there's a global group G, which is spontaneously broken at scale lambda to an unbroken subgroup H. Now, conveniently, I plugged in the value for the VEV would be F, so exactly this dimension for parameter that was floating around. And let me first assume that the unbroken group H contains the electroweak gauge group completely. So this unbroken group also contains our SU2 left cross U1 from the standard model. The Nambu-Goldstone bosons are fluctuation around this vacuum. So the Nambu-Goldstone bosons live in the coset, so G over H. So these broken generators will contain the Nambu-Goldstone bosons. So if you want to describe the fluctuation of phi of x, then you will multiply with this coset, the coset generators. One of these Nambu-Goldstone bosons will be the Higgs. So the reason why the Higgs is light is because it will come from explicit breaking of the global group, but it only arises at one loop. Right? So that's the non-trivial thing here. The one loop, like the Yukawas, will only give the mass of the Higgs at one loop. So that also explains why the Higgs is lighter than the scale lambda of the strong interaction. Now, what happens in the composite Higgs models is a little bit, it's a variance of what I was just telling you. The difference is that in the group H that contains the electroweak symmetry breaking is not really orthogonal to the VEV, right? So, in other words, the VEV is slanted a little bit, so there's an angle theta between this direction which would not break the standard model electroweak group and what really happens in reality. So there's a rotated vacuum in one direction, there's an F sine theta component, or in F sine delta in one direction, and this is the direction of the Higgs field. Right? The Higgs field is the one which obtains VEV from the low energy description. Right? So electroweak symmetry is broken only by this projection on the Higgs direction. So now we have an important relation, is that the VEV, the electroweak VEV, is the VEV of the strongly interacting sector times this sine theta. So the y is small, the VEV is small because this theta is small. That would be the explanation of why there is a disparity. Okay. So let's go to the more explicit model. So we'll only talk about the minimal composite Higgs models. Now what we want is that the low energy theory will have a custodial symmetry. So the custodial symmetry is there so that the electroweak radiative corrections are of the right size. So we need to have a remaining SO4 global symmetry. Now the minimal choice which will give us the Higgs, so a doublet of the electroweak symmetry, is that the global symmetry is SO5. So the breaking is SO5 to SO4. To understand this, let's do the counting of the degrees of freedom. So how many Nambu-Goldstone bosons do we have? So there is n times n minus 1 over half generators for the SON. So for the SO5 goes to SO4, we start with 5 times 4 divided by 2 generators in the beginning. We have a remaining SO4, so that's 4 times 3 divided by 2. and the difference is 4. So you have 4 degrees of freedom, 4 broken generators. 4 broken generators means that we have 4 number-Goldstone bosons. It's exactly the number of degrees of freedom we need to have our Higgs doublet. So the Higgs doublet has 4 degrees of freedom, 4 real degrees of freedom, and these are exactly these 4 number-Goldstone bosons. So the Higgs doublet that we see is exactly the number-Goldstone boson of this global symmetry breaking. So all the number-Goldstone bosons are part of the Higgs doublet, so in this minimal septa, there are no leftover pions. So this will be the light degrees of freedom. Okay, so now we should understand how this number-Goldstone boson couples to the W and the Z. So here I'll use a shortcut that in many electroweak symmetry breaking models that we saw so far, the coupling of these Higgses, like in a 2 Higgs doublet model where we had a small h and a capital H, there's a sum rule. The sum rule is that the couplings to the W or the Z, the squares of these couplings should sum up to the standard model one, right? That was the sum rule that we saw in the 2 Higgs doublet model. It's valid more generally for many models. In particular, it also applies here. Right? So now, if you want to have if you want to know what the couplings to the Goldstone boson is, well, we need to see what the coupling is to this. What the coupling is to the heavy degrees of freedom or the strong interaction. So the part of the mass which comes from the strong interaction is this guy here. So that will be the coupling to the strong interaction. So the sum rule is the coupling to the strong interactions plus the Goldstone boson squared. The sum of squares give you the standard model. Or if you're interested in the size of these couplings, you subtract this piece, and you see that the coupling to the W and the Z normalized to the standard model is 1 minus V squared over F squared. Okay, maybe this was a bit heuristic. Probably in order to believe it, I would have to go explicitly, but it's a shortcut that you can see that roughly something like this could arise. In the end of the day, there are 2 important things to remember. No? This argument was quite general, so this derived quantity will be a very general result for the composite Higgs models. The fact that you see 1 minus V squared over F squared is something which is quite model independent. It only depends on what you will assume for this. If you don't have some higher representations for the Higgs. And furthermore, it's always suppressed. So the coupling to W and Z is always reduced. Right? So the pseudo-Goldstone boson, the Higgs as a pseudo-Goldstone boson, will always couple to the standard model, W and Z with the suppressed strength. And the suppression goes as V squared over F squared. So you're quadratically sensitive to the F squared. So if you push F to be bigger and bigger, this will become closer to 1. It will go as 1 over F squared. So it will decouple relatively quickly. Okay. Now the next ingredient is how you couple to the standard model fermions. Now this is a more model-dependent part of the story. It really addresses on how the masses of the standard model fermions are generated. So pictorially we have this strongly coupled sector. There's our Higgs. Now there's other fermions sitting there. At the end of the day, you will have the resonances composed of these fermions, and these resonances will be in the form of either the vector resonances, or you will have fermionic resonances depending on the model, right? And then there's our standard standard model which have elementary fields, the standard model quarks, the W, and the gamma. And you need to somehow relate the strongly coupled sector to the standard model. You need to give the standard model fermions masses. There are different ways of doing this. In some way, you need to couple to the strong sector, because the strong sector breaks electric symmetry, and then you will generate the fermionic masses. So I won't go through all the possibilities, but we'll immediately focus on the partial compositeness. So here the Higgs couples to composite fermions, and these are in some representation of the global group. In our case, this was SO5. And then standard model fermions mixed with the composite fermions. So the picture is the following. So you have a Higgs. This couples to the composite, the fermionic resonances, the left and the right chiralities, and then you have mixing to the standard model fermions. So the blue bold will denote the composite fermions, and the thinner lines are the elementary particles. Now, generically, the larger the mixing, the larger the mass of the standard model fermion. So, if all these couplings in the Higgs, between Higgs and the composites are roughly the same, then the difference in the standard model masses will come from the mixing itself. So, smaller mixing would mean smaller masses. Now, top in this story would then be the most composite standard model fermion because it has the highest mass. So we look into a toy model. So we'll take only the third up generation, so the top and the Q left. And then in the strong sector, we'll also keep the minimal setup, so 2 Dirac fermions, 1 weak doublet Q and a weak singlet T. So exactly this picture that I had before. A weak doublet Q and a weak singlet T. Okay, so let's see what governs the mixing. So the mass terms before electroweak symmetry breaking, since these are Dirac fermions now, you can just write an explicit mass term there. And then you have a mixing term with dimension full parameter lambda, which couples the standard model fermions, the elementary, with the composites. The mass eigenstates will then be obtained by rotating from this gauge basis to the eigenstate basis, the mass eigenstate basis. Now I'm only looking at the left sector, and the mixing angle which sits here is roughly this the mixing coupling divided by the mass. So a heavy state is then roughly of the size of M, which sits here. And you also have one of the two states is massless. Right? This will be the standard model fermion. So it's the elementary with the cosine theta minus the composite times the sine theta. So if theta is small, this piece will be 1, and the standard model fermion will be completely elementary. If theta, sine theta is 0, for theta being small, then there is no composite. If you, however, have large mixings, then the standard model fermion is composed of elementary and the composite mixture. Okay. Now, similarly, you would write down for the right-handed fermion. So these mixing angles are governed by this dimension full parameter lambda, we set in the Lagrangian. The setting for the right-handed sector. And as I said, large mixing you will obtain if these dimensional full parameters are of the size of the masses of the resonances. Right? So then we have large mixing. Furthermore, you see that the left and the right-handed sector are in principle decoupled, so you could have right-handed mixing large, but the left-handed mixing small. Right? Now, the composites coupled to the Higgs, so this is this part of the couple.